In this video, I'll be talking about what is combination. And before I start the definition of the combination, let me to recall what is permutation and the circular permutation that I did in my last video. Link added in description. So for the permutation, let us consider permutation, which means we are talking about arrangement and the ordering of the object. So for this, let's consider a set A, and here I'm considering the distinct object A, B, C, D. And suppose if I want to consider permutation of elements of A, permutation of elements of A is 4 factorial. As we know that there are 4 objects in this, or you can say the 4 letters are there, and of course this one is without repetition. So we need to be very specific again. If it is with repetition, the answer would be different. So we want to permute 4 objects. We want to arrange these objects at 4 places. To place one of the object from the set A, there are 4 choices, and then to place another object at the second place, there are 3 choices, and 2 and 1 followed by. So this we follow usually by multiplication principle. So we can simply say using multiplication principle. Similarly, if this question was with repetition, so if this question is with repetition, in that case the same procedure we will follow. But for the first case, there are 4 choices, A, B, C, D, any letter can come at this place. And similarly for the second place, we also again have 4 choices because we have allowed with repetition, and then 4, 4. So this would be 4 to the power 4 if the question says we want to permute with repetition, and again this is using multiplication principle. And now suppose I have a question, what are 3 permutation of A? So we know that in the set A there are 4 objects. Out of 4 we have to arrange 3. So in that case we used this concept as 4p3. So we first take out 3 objects and then we permute them. That means which comes in the first order, which comes in the second order, and this is 24. This in detail, which are the relevant permutation, I have written this in the last video, link added in description. Now if I look this same example in terms of circular permutation, so for the circular permutation, let me to consider the same example, and we can see the difference again before we move to combination. So this is A, B, C, D, and if I want to take all elements, so if it's simple circular permutation of A, so circular permutation of A means I am considering all objects. So this is 4 minus 1 factorial, that is 3 factorial. And here I have explained, because it does not matter which is the first object or the last object, they sit on the circular. So whichever may be treated as the first object or whichever may be treated as the second object, because they are in the circular. So we do not, what is important in the circular permutation is the relative position. So we can see there are 3 relative positions. So if you fix an element A, then for the other one there are 3 relevant positions in which you can place. So this means 3 factorial ways are available. And again this, all the relevant one, you can see it in last video. Now if the question is 3 circular permutation of A, so now I am placing 3 objects of A. In this case I am using this notation for circular permutation 3. So for P, P is used for, notation is used for the permutation. Q, I am using the notation for the circular permutation. And out of 4, I am first arranging 3 in a circular table or the round table. This is 4p3 divided by 3. Because if you choose 3, it's important that we are considering their relative positions. So in general, we can have NQR. This is same as NPR divided by R. Now these 2 things I have already covered in my previous video, but before I wanted to define combination, I have recalled it. Now the same example we will extend it to combination. So if I extend the same example to the combination, and in the combination I use the notation C, so we can use notation NCR. So here when I say use the notation NCR, so this is the number of object, and R is the selected object. We can say selected objects. Now in this case, let's again consider A, which is A, B, C, D. And now if I choose 4 elements of A, so which means all elements of the object of the set A is selected, and this can be done in only one way. So in the notation, we will use it as 4C4, and later on I'll give you the formula also 4C4, which obviously everybody is quite familiar. That is n factorial upon n minus r factorial into r factorial. But we will see this in coming step. And now 3 combinations of A. So suppose that set A has 4 elements and I only want to choose 4. So out of, let's say in a box you have 4 items, 4 objects, and you want to select 3. So in this case, so based on this notation, we will say it is as 4C3. And what are the relevant combinations? So we can see the relevant combination will be ABC. Either we select ABC and then we have ABD, and then we can have ACD, and then we can have BCD. So this is the combination. Whereas in the permutation, the order does matter, in which A comes at the first place or B comes at the first place or C comes at the first place if I look at the first set. But in the combination, ordering does not matter. So we can see in this remark what is the difference between permutation and combination of set of object. Permutation is an arrangement of certain object in which ordering is considered, or we say ordering is important, whereas in combination it is just a collection or the subset of sets of the object whichever has been considered. So now we are ready to write a formal definition of the combination. So let A be a set of n distinct objects. A be set of n distinct objects. And then we want to define what is combination. So a combination of the set A, a combination of A, and so I'm just putting commas here so that it's inverted commas, so that it's the set that I'm referring. Simply a collection, or this is a subset of A. This is simply a subset of A. And we can further define an R combination. When I say R combination, which means we have selected R elements out of the n elements which are available in the set A. And here also we notice that these are distinct objects. If these objects are not distinguishable, then we have to modify the definition, or we have to select our way of selecting those object depending upon what is the problem given up. So while discussing in the multi-set, I will again come back to these points in my coming up videos. But at this moment, R combination, and here of course R lies between 0 and n. This of A is an R element subset of A. R element subset of A. So we need to consider again a subset of A in which there are R elements. And now to derive the formula for NCR, let us make a note of the calculations. We can simply write that using the multiplication principle. In the permutation, I have explained that ordering is important. So if I look at the permutation, this is simply NCR, because we first select the object and then we permute them. So to permute our object, there is a possibility. So to permute our object, we have to take R factorial into the consideration, because there are R object. So for the first object, there is an R possibility. For the next object, we have R minus 1, and we continue. We know these are distinct, so this will become R factorial. So NPR is same as NCR into R factorial. So we can simply say NCR is same as NPR divided by R factorial. And hence we derive to this formula, that is n factorial upon R factorial into n minus R factorial. And of course, here we are considering R lying between 0 and n. And now we can note further that NC0, this is of course 1. We can also note that NCN, this is 1. And in case we have NCR, which we just have explained, n factorial, R factorial into n minus R factorial. This is same as n factorial. And if I keep this n minus R factorial here, let's keep this as here. And this R factorial, I am writing add 1n and subtract minus R factorial. So this term is same. And now I can write this as n C n minus R. So if I look this one into the definition, into this format, into this notation, NC n minus R. So from here we can see that n choose NCR. This is same as NC n minus R. We can also, or we can use this notation also, n choose R. This is same as n minus r. So this is another way of notation that we can use for the combination. So in case I want to find values of n, choose r, and of course r lying between 0 and n. So suppose that on one side I consider n and on another side I consider r, and I'm just creating a box here, let's say like this one, and then we have 0, 1, 2, 3, and we continue the values some here, then we continue 0, 1, 2, 3, and we continue the value here. So obviously each value 0, 0. So the first place that I want to write value here, this means it is n, r, and in this case the value is 0, choose 0. We have just seen if it is 0, choose 0, this value is 1. So we place here this value as 1. If it is 0 and then we want to calculate 1 here, so we will not calculate these values because r cannot exceed 0. So these values will not be calculated. So we'll keep this place as blank. Then for this first case, this is 1, choose 0. So if I take 1, choose 0, so this value is also 1. If I take 1, choose 1, this value is also 1. And similarly, the next value, these cannot be calculated since r is exceeding the n. So now we move forward. So this is 1. In case you want to choose 2, and then here it is 1. So if you want to select 2, choose 1. So you can calculate this from the formula. So this is 2 factorial, 1 factorial, 2 minus 1 factorial. So we have here 2 factorial upon 1 factorial into 1 factorial, and we know this value is 2. So this is 2, and then similarly 2, choose 2, this is 1, and we continue filling the expression. So we note in the same way, if I continue this table, we know if I have to calculate 6, choose 2, this will be same as 6, choose 4. Now this leads to a very interesting identity, and this identity we further note. Let me to write down into an example, and then we further give this into the form of a proposition. So if I want to calculate 8, choose 5 plus 8, choose 4, we note again from the table that this value is coming out to be 56, and 8, choose 4, this value comes out to be 70. This is 126. And we notice in the table that this is 9, choose 4. This is what we call it as Pascal's identity. Now Pascal identity proof I will do in the next video. There are two ways. One is simply using the formula. Another is combinatorial approach. How do we prove this using the combinatorial approach? So this I will cover it in my next video. But now let me to take some examples so that we know some example based on the combinations problem. So in this example, the question starts saying that there are 2 to the power 7 binary sequences. So the example state by giving the statement that there are 2 to the power 7 binary sequences of length 7. So this is although justifiable. Why we can say? So we want to have a length 7, 1, 2, 3, 4, 5, 6, 7. Now since we are talking about binary sequence, so there are possibility either we are talking about 0 and 1. So there are two choices. So there are two ways for the first place. Similarly, because in the binary sequence any digit can repeat, so again there are two choices in the second position, there are two choices in the third one, and we continue, there are two choices for the last also. So we know that there are 2 to the power 7 binary sequence of length 7. Now the question is, how many such sequences are there which contain 3 zeros and 4 ones. So now this question is, again we can see in this question, the total length is 7. So we first place the length 1, 2, 3, 4, 5, 6, 7. And in that it has been already said that there are 3 zeros. So if I say randomly place 3 zeros, then obviously at the remaining places you have to keep 4 ones. So here we will simply say out of 7, the length is 7, I want to select 3. Or you may simply say out of 7 you will select 4 ones. So both of these are equal. So here you can even put it as equal. We have just seen because of this equality that NCR is same as NC n minus R. So we will simply say such binary sequence are given in the form 7 choose 3. These are binary sequence in which we will have 3 zeros and 4 ones. In this example, we want to know in how many ways can a committee of 5 be formed out of a group of 11 people consisting of 4 teachers and 7 students. So there are different conditions. In the first condition, they say there is no restriction in the selection. So here, when there is no restriction in the selection, this is a simple question of the combination. So we know how many total members are there. The total members are 11. So you can consider that in a room there are 11 people, and out of 11 people we want to select 5, any 5. So 11, choose 5, so we'll have 11 factorial, and then we got 5 factorial divided by 6 factorial. We will solve this up and we get 462. Now for the second case, we want a committee must include exactly 2 teachers. So obviously here we first select 2 teachers. So let us first select 2 teachers. And so you have to select 2 teachers from the available teachers. And so available teachers are 4. And then we follow 5 minus 2 because we have to choose a committee of 5. And 5 minus 2, that means the remaining 3 or 3 students from the available students from 7 students. Now you see that this is like a sequential approach. We first selected teachers because there is a condition, and followed by we selected the student. So here using the multiplication principle, 4C2, and then we have selected 3 students from 7. So this gives me 6 into 35, that becomes 210. And here we can simply say using the multiplication principle. So the basic 2 counting principle comes again and again. So we have done these 2 basic counting principle in my last video, link added in description. We did this 2 basic counting principle, addition principle and multiplication principle. Now in the third case, the question says the committee must include exactly 3 teachers. So here it says the committee has to include exactly 3 teachers. So obviously we will first take 4C3, and then we will take followed by 2 students, that is 7C2. This is equal to 4 into 21. This is equal to 84. And suppose in this third part, instead of exactly, let's say if this question was at least. So I'm just putting here, or if question ask for at least 3 teachers. In this case, the teachers in total, there were 4 teachers. So either they can have 3 teachers or they can have 4 teachers, because I am asking the question for at least. In this case, if there are 3 teachers, so we will have, if 3 teachers, then we will have the same case, 4C3 into 7C2, and this becomes 84. Or there could be 4 teachers, and in that case we will have this 4C4 into 7C1, because the total committee was for 5. So obviously out of 7 we have to choose only 1 student. So this is 7. And now using the addition principle, because there is a choice between the initial selections. So using the addition principle, we can add 84 plus 7, that is 91 ways. So this way we can modify this question depending upon what has been asked. Now in the fourth question, it says a particular teacher and a particular student cannot both in the committee. So we will consider this as a single object, and then we'll try to solve this fourth problem. Let's say here T1, this is the particular teacher. I'm just calling any particular teacher which has to not been there simultaneously with that student. And let's say S1, this is the particular student that we are talking. So we do not want that in this committee, T1 S1 becomes a part of the committee. So this pair should not be there simultaneously. Individually T1 can be there in the committee, individually S1 can be there, but both should not be there in the committee. That is the question demand. So here we consider T1 S1 as a single entity, or you can simply, for the consideration, you can say that I will consider this as a single object once I have to consider this from the selection. Now once we have considered this as a single committee and we want to choose, of course, 5 people. So in this case, we will first consider a committee in which T1 S1 is a member, and then we will subtract from the desired in which they are not a member. So here we consider a number of ways to form a committee of 5 including T1 S1 is 9C3. that is 84. Here 2 members are already covered in the committee. So we can see that in 5-member committee, 2 T1 S1 they are already member. So first I am choosing when they are already member simultaneously. So T1 S1 is already there, 2 members are already selected, and the remaining 3 members that we are taking out from this combination. So, and we have also considered that this as a single entity. So there are 9 out of 11 we have already selected 2 members. So the remaining members are 9. So remaining members are 9, and out of remaining 3 have to be selected. So that is 84. Now using the complement principle, so what we will do, total number minus the committee including T1 S1. So this, when I including T1 S1, this particular teacher is including. So total number we have calculated in the first case, that is 11,500, and here you can mention using complement principle. So total is 11,500 minus committee including T1 S1, that is 9,300. So this will give me the answer as 462 minus 84, that is 378. We can look this again if this particular point is not clear. 9, because 2 members are already taken up. So out of 11, 2 are already selected, that is 9. So the remaining members are 9. So that is why I have selected 9 here. And we want to make a committee of 5 people. So out of 5, since 2 are already selected, 3 are more to be selected. So that is why we selected 3 here. So 9C3 is 84, in which T1 S1 are already every time they are member. Now we subtracted this from this one because we wanted that this is the committee which do not select T1 and S1 simultaneously. So we can say they are not simultaneously a member. So that is the answer 378 for the last part.